hypothesis test for a single mean. So, just like with the proportions, our null and our alternative hypothesis are formed just like before. Instead of doing a z-test, we're doing a t-test. Right? Your test statistic is your statistic minus your null value over your standard error. But because our standard error requires the standard deviation of the population, and we don't know that, and we use the sample standard deviation to approximate it, we're doing a t-test, just like we did a t-interval for the mean for a confidence interval. Find the p-value from the table. We're not going to do that. You have a function on your calculator that's called tCDF. It's like the normal CDF, but for a t. That. Right? Lower bound, upper bound, degrees of freedom. And then you state your conclusion. So, same four steps as our hypothesis test for proportion. The only real difference is that it's a t instead of a z. So the heights of 25 students have a mean of 186 centimeters with a standard deviation of 3 centimeters. What is the standard error of the distribution of sample means? Right, your standard error is Sx over the square root of n. So Sx is 3, and n is 25, so 3 over 5 is 0.6. Assuming the population mean height mu is 185, what is the t-test statistic? So our specific formula for t for a single mean is x bar minus mu over Sx over the square root of n. So x bar, this was our x bar, was 186 over, or 186 minus our mu, which is telling us is 185, over Sx over the square root of n was 0.6. So we get 1 over 0.6, which is 1.67 for our t. And then the probability of getting a sample mean of 186 or higher is you do tCDF of 1.67, 1E99. And how many degrees of freedom? Again, your degrees of freedom is n minus 1. So n minus 1 degrees of freedom, our n is 25, our degrees of freedom is 24. And you put that into your calculator, and it's going to give you a p-value of 0.54, which we would reject the null at the alpha equals 0.05 level. And there's your tCDF. Let's do a full hypothesis test here. A sample of 12 golden retriever puppies at birth has a mean weight of 15 ounces and a standard deviation of 1.5 ounces. Perform a hypothesis test to determine if the average weight of newborn golden retriever puppies is different from the average weight of yellow lab puppies, which is 14.2 ounces. Use a significance level of 0.05. So this is a population mean for the yellow lab puppies. So this is a single proportion, a single mean, a hypothesis test for a single mean where we're comparing to 14.2. It's not a difference of means because this is a population mean, not a sample mean. So state the parameter is the average weight of golden retriever puppies. Retriever puppies at birth. Our statistic is that X bar is 15 ounces. Our null hypothesis is going to be that mu is 14.2 ounces, right? Our null is that the golden retriever puppies weigh the same as the yellow lab puppies. Our alternative hypothesis is that mu does not equal 14.2 because it says different and doesn't indicate the direction. So it is a two-tailed test, and so we're going to use a not equals here. And then our alpha is 0.05. We do our plan step. We name the procedure. It is a one sample t-test for mu. Again, one sample because we only have the sample of golden retriever puppies. This is the population parameter that we're comparing to. It's not a sample. One sample t-test for mu. We check our conditions. Random. We're going to assume that 10%. 12 is less than 10% of all golden retriever puppies. And our normality condition. We don't know the population shape. We don't know, our N is not at least 30, so we should check for skew and outliers. We don't actually have the data, so we're going to assume that that one's good. Our do, right, our general formula is the test statistic equals the statistic minus the null value over the standard error, which for a hypothesis test for mean means that t is x bar minus mu over sx over the square root of n. And our x bar is 15, our mu is 14.2, our sx was 1.5 over the square root of 12. And you put all that into your calculators, and you calculate it, and you get a t equals 1.85. We should also sketch our curve. So if the mean is 14.2, we got 15. We want to see if it's at least 15 or the same difference in the other direction. This was plus 0.8, so 14.2 minus 0.8 would be 13.4. And this was a normal distribution with a mean of 14.2 and a standard deviation of whatever 1.5 over the square root of 12 is. And then we calculate our p-value. This is a two-tailed test, so it's going to be the probability of a t that is, technically there should be a capital T, a t that is at least 1.85 or t is less than negative 1.85, which is 2 times the TCDF of lower bound 1.85, upper bound 1E99, degrees of freedom n minus 1, which is 11. And I thought I put that in there, but so you do that and you multiply it by 2 and it is 0.091. Our conclusion: if the null is true, that mu is equal to 14.2. There is a 0.91 probability that we would get a X bar that is of at least 15 ounces or less than 13.4 ounces, purely by chance. Because our p-value of 0.091 is greater than alpha of 0.05, we do not reject the null hypothesis, and we do not have convincing evidence that the mean weight of golden retriever puppies is different from 14.2. There we go. That's our conclusion. One more. Mr. Betts buys 8 fun-sized bags of M&Ms. He finds they have an average of 45 M&Ms in each bag with a standard deviation of 5 M&Ms. Conduct a hypothesis test to determine if Mr. Betts can conclude that fun-sized bags of M&Ms contain more than 41 M&Ms. Use a significance level of 0.05. So, state our parameter is the average number of M&Ms in all fun-sized bags. Our statistic, our X bar was 45 M&Ms. Our null hypothesis is that the actual average is 41. Our alternative, right, more than 41. Mu is at least 41, or it's greater than 41. And our alpha equals 0.05. We name our test. It's a 1-sample t-test for mu. We check our conditions. Random, we can assume it's random. 10%. 8 is less than 10% of all bags of M&Ms. And our large counts are, we don't have at least 30. We don't know the population shape. So we should check for skew and outliers. In the sample data. We're going to assume that there is no skew or outliers in the sample data. So we're good here. Our general formula is the test statistic equals the statistic minus the null value over the standard error. For a mean, that's t equals x bar minus mu over sx over the square root of n. We plug our numbers in. That's going to be 45 minus 41 over 5 over the square root of 8. And that gets a t of 2.26. This is a one-tailed test because we said mu, our alternative is that mu is greater than 41. So if the mean is 41, what's the probability of getting 8 bags with a sample mean of 45 or greater? This is a normal with a mean of 41 and a standard deviation of 5 over the square root of 8. And then our p-value is going to be the probability that t is at least 2.26, which would be TCDF, with a lower bound of 2.26, an upper bound of 1E99, and 7 degrees of freedom, which is 0.029. So we conclude, and I'm definitely going to run out of space for the conclusion here, but if our null is true, that mu does equal 41, there is a 0.029 probability that we would get an x bar of 45 or greater purely by chance. It's the first part of the conclusion. We'll go up here. Because 0.029 is less than our alpha of 0.05, we reject the null hypothesis and do have convincing evidence that the mean number of M&Ms in all fun-sized bags is greater than 41. There we go. All right, so inference for a sample mean. You check independence of the observations, so a random sample and 10% condition. And then we check our normality large counts. Either our n is at least 30, or the population is nearly normal, or no skew or outliers in the sample. Our general formula is that our test statistic, which in this case is t, is the point estimate minus the null value over the standard error. Your degrees of freedom are n minus 1. And that's hypothesis testing for a single mean. Woo!